I'm Jancy Despain with Bright Idea Tutoring. This is part 5 in a 6-part series on aldol reactions. In this video, I'm going to teach you how to recognize intramolecular aldol reactions and to predict products using the techniques that you learned in videos 2 and 3. Thanks for watching. This is an example of an aldol reaction that just looks a little bit different than what you're used to. Here we have one molecule that contains 2 ketone or aldehyde groups. This is called an intramolecular aldol reaction. And we know that it's going to be intramolecular, again, because one molecule contains 2 reactive groups. And when that occurs, these 2 groups are going to react with each other and form a ring structure. And in this case, we already have one ring structure, and we're going to form a second ring structure. And when you see one like this, I guess a lot of students tend to get a little freaked out, but you're going to follow the exact same rules that I've already taught you for predicting products for the other types of aldols. Our first step is just to choose which alpha carbon is going to become the enolate. So we have an alpha right here and an alpha right here. And they're both identical. So in this case, it doesn't matter which one becomes the alpha. So I'm just going to pick this one. I'm going to pretend that a proton has been removed from it, which means that it's going to become a carb anion with a negative charge. Then I'm going to pretend that this carbon has attacked the other carbonyl, which means I'm going to draw a bond between this alpha carbon and the carbonyl, and I'm going to push these electrons up onto the O. Then I'm going to redraw this molecule, and of course redrawing it with this bond shortened and everybody looking a little bit more attractive. So this is still a 6-membered cyclohexane ring. And over here, this is a 1, 2, 3, 4, 5-membered ring. So there's a nice 5-membered ring. At this corner, I've got this little aldehyde group sticking off. At this corner, now I've got a single bond to O, which I'm then going to protonate. And at this corner, I just have 2 hydrogens. And as a last step, I need to think, was this done in heat, or is this conjugated, like a conjugated system? Because if so, I need to go on and do my elimination step. But there's no heat and there's no conjugation, so I'm going to leave it looking just like this, the beta hydroxy group. So we're done. Let's take a look at another example. Here's another example of an intramolecular aldol reaction. And again, we know it's intramolecular because we have one molecule with 2 carbonyls. So we know that one alpha carbon is going to attack the other carbonyl, and that's going to give us a ring structure for our product. Just like before, our first job is to decide which alpha carbon is going to attack. And normally we would let our base decide this. Remember that like an ethoxide or hydroxide base is going to pick the more substituted alpha carbon, and if we had LDA, that would pick the less substituted alpha carbon. But it's different when you have an intramolecular aldol, because what happens is with intramolecular, it's the size of the ring that matters, not the type of base you have. Let me show you what I mean. If we were going to go with ethoxide, ethoxide wants to choose one of these more substituted bases, or more substituted alpha carbons. So let's just say it would pick this one. I'm going to turn this one into my alpha, and I'm going to let it attack my other carbonyl. Now I can't directly draw a bond here, so I'm just going to let it come underneath and attack and push these electrons up onto the O. And let's look at how many carbons are in that ring. There's a total of 1, 2, 3, 4. And a 4-membered ring isn't very thermodynamically favorable. A 4-membered ring is like a square. It has 90-degree bond angles, and carbons don't want to make 90-degree bond angles. This doesn't really make sense. What makes a lot more sense is to use one of these less hindered alpha carbons. If we let this carbon become the alpha carbon that's going to attack, and it attacks here at this carbonyl, we are now going to have 1, 2, 3, 4, 5, 6 members in our ring. And a 6-membered ring is much more stable. In fact, aldol condensations almost always form 5- and 6-membered rings. So when you're choosing what size of ring to form, 5 and 6 are preferable to obviously 4 and 3-membered rings, but 5 and 6 are preferable even to larger rings like 7 and 8. So when you have a chance, always choose a 5 and 6-membered ring with an aldol reaction. Now we need to focus on how to do a good job drawing this product. If I was going to draw my product, I would create a numbering system. Carbon 1 attacked carbon 2. Here's 3, 4, 5, and 6. So I know I'm going to make a 6-membered ring. So here's my 6-membered ring, and I've just created a random numbering system for it. All right, I know that carbon 1 is bound to carbon 2, and on carbon 2 I've created a single bond to O, which is then going to be protonated, and carbon 2 also has a methyl group. Carbons 3, 4, and 5 are clean, and carbon 6 has a carbonyl. And just to confirm, we have a hydroxy group and an O, a carbonyl, and there are O, 1, 2, 3, O, 3 carbons between the O's. Now, never forget to check for conjugation or heat. In this case, we do have heat, so we need to make sure that we complete the condensation step at the end. That means we remove our hydroxy group and fill in the double bond in the alpha-beta position. This is our final reaction product. Do you think you're ready to try one on your own? This one's a little bit tricky, but I've given you some hints. Your first hint is don't forget to check and make sure that you create a 5 and 6-membered ring, not a 4 or a 7 or an 8. And your second hint is always at the end, don't forget to check for the presence of heat or conjugation before you finish up, because you got to make sure that you're going to do an elimination product if that's a possibility. All right, hit pause, try and do your best to predict your final product, and then let's come back and see how you did. How'd you do? This is the final product I came up with. Here I chose this alpha carbon to be my attacking carbon. I drew a bond between this one and my carbonyl and pushed the electrons up. Of course, I chose this one because it makes a 5-membered ring, not this one, which would have made a 7-membered ring. Here's my 5-membered ring product. There used to be a hydroxy group here, but I went ahead and completed the elimination because this is a conjugated product. So even though we didn't have heat, we do want to continue on and complete the elimination so that we can have full conjugation. And your product may look just like mine, but be flipped vertically. As long as you have the ketone group coming off here and a 5-member ring, you're probably fine. If you want one more example, here's one that you can try. Let's predict products and see how you do. This is what my product looks like. You'll notice that I left the beta hydroxy group and did not continue with the elimination step because there's no conjugation and there was no heat present. I used this alpha carbon rather than this one to attack my carbonyl because I wanted to create a 5-membered ring, not a 7-membered ring. If you have any extra questions, hit me up in the comments or contact me through my website. I'd love to help you. Thanks so much for watching. Don't forget to like and subscribe.